shut up and sit down.
You're listening to Electrician Live with your host, Paul Abernathy. Well, hello everybody. Welcome to Electrician Live. My name is Paul Abernathy, your host, and welcome to the podcast for everybody listening over on electricianlive.com. And those that are listening to the podcast stream live, we also have our people following over on the video at youtube.com/master the NEC. Want to thank you for coming to tonight. Believe it or not, I was actually out and about today, and and actually, I know this is going to be embarrassing, but I actually almost forgot about the podcast tonight. And I was like, what? I almost forgot. So anyway, I was able to get everything put together really quickly in order to get here so we could have this podcast again as we do it every week on Saturday evenings. And we do it at 8 p.m. Central Standard Time, where we broadcast Electrician Live. It is a podcast, so people that are listening over on our podcast network, it's also being streamed through at least 15 other type of networks, Deezer, Spreaker, all these other types of things. So welcome, definitely welcome. So we have also followers again, and I encourage you that if you listen to our podcast, that you also want to get the video flavor by going over to youtube.com/master the NEC, and you can join in and see the video presentation, and you'll see people that are in the room that will be sharing comments, and we'll interact with them. For those that are following on the podcast, because you have to remember that this is Saturday night, it's a podcast, but I want to make sure that I paint a picture visually so people following along in the podcast can understand what's going on and not just designed for the people that are watching the video. Okay, so, and you can watch this rebroadcast later, provided YouTube doesn't go haywire and something happens and everything goes wonky. Hopefully that's not going to happen. So anyway, tonight's episode on Electrician Live is we're going to talk about single-family dwellings, and we're going to talk about standard calculations. Why standard calculations? You're probably thinking, in the real world, nobody uses a standard calculation. Well, when you're doing the neutral calculation, you're going to need to know how to do the standard calculation. Okay, you can't use the optional method for that. In the real world, we're going to use the optional method simply because it is much easier and it's going to result in a smaller service. And that's, as electricians, we're all about cost effectiveness, so that's the route we're going to go. In the real world, for an exam, for example, you need to know how to do the standard method. So we're going to go over that tonight and talk a little bit about it, give you some scenarios, have some conversations about it, and we'll probably interact with some of our people that are over on our video stream. Again, youtube.com/master the NEC. Make sure you join us if you're listening over on the podcast. Real quick, we're going to give some shout outs to people that are in the room. We want to give a shout out also to Danny Harris for becoming a VIP member over on our Patreon. Thank you, Danny, for doing that. And I'm probably going to make sure that I also shout out to another Patreon member that I totally want to make sure. Mr. Lucky, thank you for being a Patreon member and supporting us. Santos Esquivel, and I'm going to probably butcher that, Santos, but thank you also for becoming a VIP patron member. And hopefully that you're enjoying our 2020 episodes, and we'll have more and more and more of those coming out as we move into this year. Okay, so there's a lot of stuff there, and the newsletters are up there as well for those that don't subscribe to the newsletter, which is a cost thing. But over on the actual Patreon, it's included in your subscription, and a new one gets uploaded every month, okay? I uploaded it today just because it is, again, leap year, so I figured why not? So we did it. I want to say howdy to everybody that's in our video stream. Robbie, Danny, Elias, 12 Mandingos, thank you for coming. Tim Johnson, how you doing, Tim? Thanks for coming. And of course, all of you out there that's listening to the podcast stream, we have monthly a total of over 300,000 unique listeners to our podcast. Not so much the videos. I wish we could get that number up, but you know what? The podcasts seem to people love podcasts. So anyway, so thanks all of you for actually coming to the show tonight. Okay, so let's kind of get into it a little bit. Now, tonight's show is not so much just exam prep, and I'm going to be leading because it is a podcast, and we're doing a video stream of the podcast. I'm like the Howard Stern of electrical, or maybe the Rush Limbaugh. Poor Rush. Prayers go out to Rush. But anyway, we're going to actually try, and I'm going to do my best to convey this so people that are listening to the podcast can get the understanding and the flavor, okay? And we might dip into the Fast Tracks program, and I will do my best to display that to you. But I'm telling you right now, if you're listening to the podcast while you're driving in the car, don't wreck. I know I'm exciting and all that, but don't wreck. When you get home, go watch the video to get a better flavor of what we're going to talk about tonight. All right, so some of you might be familiar with my single-family dwelling calculation standard method video that I did. So we're just going to kind of go over that a little bit tonight. And again, we'll talk about some concepts and some things as I explain standard methods to you, so that if you're, as we get into it, you kind of get a better understanding. So this is pretty much, if you want one of our interactive, I should mention real quick, any of our interactive during the week exam preps, make sure if you're preparing for an exam or you're just trying to hone your skills at the National Electrical Code that you join us. I do those every week. There's no set time. Usually you can pretty much bank that I'll be Wednesday evening, because that's where I do demos of our products for our company. But usually once I'm there, all the normal people that come in there, and then next thing you know, the topics go anywhere and we're all over the place. So hopefully that helps you. A lot of those get rebroadcast. Some of those don't. So anyway, check them out. All right, so let's kind of look at what we're talking about here. We're going to be dealing in single-family dwelling calculations today, because we just want to make sure that you understand each little component of it. And so it's kind of easier to follow along. So we're going to look in, where do we actually begin? Okay, so in a residential application, you probably don't have a design drawing. You probably do have blueprints that you maybe scratch on or draw on with a pen or pencil or something to that nature, right? But probably nothing overly, probably don't have any engineered drawings or anything like that. I'm pretty sure you won't. I never have. So where do we begin? So when we think about the calculation, I always like to say we need to talk about the actual space, how we develop a general lighting and general receptacle use space. And again, also I should mention, we are talking about the 2017 National Electrical Code tonight, not the 2020. I have to do a new video series for that because there are some changes that have to take place. So just creates more videos for me to have to do to teach people, okay? All right, we love teaching. All right, so let's kind of look at our scenario tonight in our example. We have a dwelling, and as it says on the screen, we're going to assume the water heater, clothes dryer, the counter-mounted cooking units, wall-mounted ovens, and electric heating is in kW ratings, and we're going to assume, and this is what the code also assumes, that it is also considered equivalent to kVA. So when we're doing these calculations, watts or kilowatts is equivalent to kVA. One thing I'll tell you, at the end of the day, we're always going to try to break everything down into VA, okay? So that's what we want to break it down to ultimately when we're doing our calculation. But again, tonight we are going to really focus on a single-family dwelling, and we're going to talk about the standard method. Because like I said at the beginning, you have to understand the standard, and we'll talk about the pieces. And that any of those pieces, for those that are preparing for an exam, any of those little pieces could be on an exam. So understanding the pieces are the important part, okay, of the whole thing, all right? So let's kind of get into a little more into the presentation. So let's look at what we've got. So we've got a dwelling unit. Its outside dimensions are 35 feet by 55 feet. and we have a front porch that's included within those outside dimensions. Okay, 7 feet by 10 feet, and it's the front porch. Okay, and it's actually, like I said, it's part of those 35 by 55 dimensions. Okay, and then we have small appliance brand circuits. In this house, there's a lot of small appliance brand circuits, but we've got 4. Interesting thing to remember as I give you little tidbits as we go through here. The code requires a minimum of 2 small appliance brand circuits. In this case, we've got 4. So remember, we're going to have to account for all 4 of them, all right? You can't just say, I'll take 2 and I'm done. Can't do that. If you got 4, you're going to deal with 4, okay? All right. So the next thing we've got here is, obviously, this house is jacked up because we also have 2 laundry branch circuits in here. Now, the code only requires 1, but we've got 2 in this house. Okay. We have a water heater. The water heater is 4.5 kW, again, synonymous with 4.5 kVA or 4,500 watts, okay, or 4,500 VA. Again, we're going to want to break all this down into VA as we move through this. So again, this is just a scenario of like what you might have in the real world. The next thing is a dishwasher. So the dishwasher is 10 amperes at 120 volts. So that's a given. We're kind of looking at the givens now. For you over on the podcast, that's why I'm reading these out so you can kind of get a feel for what we're dealing with. We have an in-sink waste disposer in this house, and it is a 0.5 horsepower at 115 volts. That's what it's rating at. The next thing that we have in this house is a trash compactor. Do we even see those anymore? I have not installed one of those in years. Back even when I was doing work, I didn't. Okay, but in this house, we do. We have a trash compactor. We need all the appliances we can get so we can do our appliances and all. So here, that trash compactor is 7.5 amperes at 120 volts. Next, we have 3 attic fans in our attic, and they're 4.2 amperes each. Very common scenario to have separate motors in the attics, okay? So cumulatively, all 3 of these represent 12.6 amperes, and each one of them are 120 volts, okay? Now, the next thing that we have is a clothes dryer. Interesting, as I'm giving you tidbits. Clothes dryers aren't required, same as cooking is not required, like ranges or cooktops. Believe it or not, they're not required by the code. But if they're in your design, you have to take them into consideration, obviously, right? So in this case, we have the clothes dryer, and it's 5.5 kW. And so we're going to be making references, obviously, to 220.54 as well, because that's clothes dryers, whereas the cooking stuff is 220.55. I think by now you probably get that. And so I'm just kind of touching on things again for those that are over there listening on the podcasts. All right, so the next item we have in this house is a counter-mounted cooking unit, cooktop. It's in the counter, and that is a 7 kW, or again, that is a 7,000 watts, or a 7,000 VA, or 7 kVA, however you want to express it. They're all equivalent when we're doing the calculations in 220. In this case, part 3 of 220. And they're 240 volts is what that counter-mounted cooking unit is. The next thing is a wall-mounted oven. And that wall-mounted oven is 6 kW at 240 volts. So we have a wall-mounted oven in our equation. The next thing that we have in this dwelling is we have electric heat. We have 3 banks of 5 kW heat, which is going to be cumulatively 15 kW of heat, okay? And that's at 240 volts. Why do we need to know all this? Because obviously we're going to have to compare heat versus the AC and take the larger, right? Okay. The next thing that we have in our dwelling is an air handler, and it has a blower motor. That's basically what the air handler is. So it's 3.2 amperes at 115 volts. Now, as we get into this, remember, that air handler is working whether or not the heat is blowing heat or it's blowing AC. It works either way. So we have to make sure that when we're doing the comparisons that we add that air handler motor in with our heat and in with our air conditioning when we're doing the comparisons. Okay, so there you go. The next thing we have, obviously, if we've got this air handler, then we've got an air conditioning compressor. That's outside, and that is 16.6 amperes at 230 volts. Okay, so we have an air conditioner compressor. And then, of course, we have what's called a condenser fan motor as well in that outdoor assembly, and that is 2 amperes at 115 volts. Okay, so we have a pretty decent little house here, 55 by 35. We got all these equations in here. So as an electrician, for me, I have to get started in it and say, okay, where in the world do I even begin? All right? Okay, so let's get into it. Now, what do we do first? Well, the first thing that we have to do with the National Electrical Code is realize that there's a table 220.12, or actually, before we even do that, we got to understand that there are instructions in 220.12. And those instructions are going to tell us for a residential dwelling unit that we take 3 VA per square foot. That is in 220.12. And in 220.12, it's going to reference us to the table 220.12. And that's where we see for dwellings, we're going to have 3 VA per square foot. You with me? Okay. So that's where we get our 3 VA. Now, interesting enough, this 3 VA in the 2017 code here, the 3 VA is going to encompass also not just the general lighting, but also the general use receptacle loads as well. That's your receptacles that are all around the wall, okay? We're not talking a small appliance. We're not talking the laundry, okay? We're just talking the general use receptacles that are around the walls and things like that, okay? And our general lighting, ceiling lights, and, recessed cans and things like that. Now, can people go wonky crazy on that kind of stuff? Absolutely. But it's considered general lighting, then that's how we're going to do it. We're going to kind of try to keep it as normal as possible. All right, so 220.12 sends us to table 220.12. That's where we get the 3 VA per square foot. We already know our values, so we're good. So on the dwelling plan that we looked at was the outside dimensions, but there was an open porch with the dimension of, okay, and since that open porch is not included in the total area, since open porches are not, because if you go look at 220.12, it says not to include open porches, okay? So in our example, it said right here that the overall dimension, okay, is 35 by 55, and then we're going to say a front porch. In our case, we'll say open porch, okay, in our case. And in that case, I need to take my overall value, and I need to take away the value of that open porch. So that open porch was 7 by 10. So 7 times 10, that's 70 square feet. So 35 by 55, that was our dimensions, and that's what 220.12 tells us to do. Take the outside dimensions. And that was 1,925. And again, if there's any math variances in here, I apologize. It's been a while since I've looked at this slide, so we'll hope everything's still right. Don't check my math. And so 35 by 55 is 1,925 square feet. Now we want to take away that 70, okay? And that leaves us with 1,855 square feet. And then we take that value times 3 VA. So that gives us 5,565 VA. And that's something that we write down, okay? We need to write that down. That's your general lighting receptacle load. So that's the first item you write down. Now, before I even mention that, I also want to say that this is kind of what it says. It says the floor area of each floor shall be computed using an outside dimensions. It says the total floor area does not include open porches, garages, or unused, including unfinished spaces that are not adaptable for future use. What does that mean? That could be an attic that has simply, you put a ladder up and you have a scuttle hole. That attic up there is not adaptable for future use. It's there, okay? I'm not adding that square foot. The other thing to remember, if this is a 2-story home, then it's per floor. In our case, this is just the one story, okay? But just remember, it is the floor area of each floor gets figured into the equation using the outside dimensions. And obviously, the second floor is the same as the first floor as far as dimensionals wise, okay? But in this case here, one floor, one value. We're not going to overcomplicate it, okay? So the first thing we wrote down was 5,565 VA. Write that sucker down because that is our first connected load, not calculated yet, pretty much connected because we got some other things that we need to do, okay? All right, so we look at it here and we've got that covered. All right, so check, everything's good. The next thing that we have to deal with, and we're going down the list, the next thing that we need to deal with is those small appliance branch circuits. And how many did we say we had? We have 4 of them, okay? So they must be included in the dwelling calculation. Now, each small appliance branch circuit is calculated at not less than 1,500 VA, okay? Now, a dwelling unit must have at least 2, as 210.11c1 will tell you, but we've got 4 in our equation, and we have to count every one of them, okay? So in our dwelling, since we have 4, it's going to be 1,500 VA times 4. So that is 6,000 VA for our small appliance branch circuits. So we want to write that down. That's our SABC, small appliance branch circuit value. Now, there is a note here. Again, it says these loads can be included with the general lighting load and subjected to the demand factors of table 220.42 as stated in 220.52b. Don't worry, we're going to do that. I just want you to remember, as we're stacking these things, you have your general lighting, okay, based on your square footage. Now you have your small appliance, and we're going down our list, okay? So if we kind of look back, now we've covered this small appliance right here, these 4. We're good to go. Now, what about the laundry? Remember, it was 2 laundry, as you see right here on the screen, 2 laundry circuits. Now, I have to have at least 1, and there's some exceptions to that rule if I'm like an apartment complex and I have a dwelling unit in an apartment complex and the laundry is not in the apartment complex or not in the dwelling unit, but it's out there and it's available to everybody, then I have some allowances. But in our example, we're just talking about a single family dwelling. I'll do additional episodes where we talk about multifamilies and all these other type of things, but just focus on this because this is the low-hanging fruit stuff on an exam, okay? And there's a lot of tidbits in here that are fodder for exams, like 1,500 VA per circuit, things like that to remember, all right? Now, so based on 220.52b, it tells us and that we have to have a laundry branch circuit calculated at not less than 1,500 VA. Okay, we got 2. Okay, got to have at least 1. We got 2. And it also tells us that we can include this also in our demand factors in table 220.42. And we'll look at that in a minute. Right now we're just stacking. We're trying to get our VA. So in this case here, it's 1,500 VA times 2. That's 3,000 VA. Okay, so we're adding that again to the list. Okay. Let's move on to the next one here, because I already had people saying my calculations are wrong, but I don't think so. Now I'm going to check this because you actually said that, and there's always one in the room. I'm just saying. So 35 times 55 is 1,925 minus 70, and that is 1,855 times 3, and it's 55,565. So this calculation is right. The next one here is, again, 4 of them, so it's 1,500 times 4 is 6,000. That one's right. And this one is 1,500 times 2, 3,000, and this one's right. So the people that are following along in the YouTube, their math is off. All right, so now let's get to what we're talking about here. So now we've got the 3 loads that we just calculated out, okay? And hold on one second. All right, so now let's bring the general lighting and receptacles, that small appliance branch circuit, and that laundry load, let's bring them together now because we want to apply some demand factors that the code allows us to do. So in this case, we had 5565 VA for general lighting and receptacle, 6,000 for our small, 3,000 for our laundry. Now, before we can apply any demand factors, we need to know what says they apply and how they apply. So part 3 of Article 220, which is standard method, is for calculating services and feeders, load calculations. And 220.42, it says the general lighting says we get the permission to use table 220.42. It's permissive. We get the permission to do it. If you want to size it based on without any demand factors and you want to end up with an overly large service, you can go for it, okay? But exams, we're always looking for the best value. And again, most people are going to use optional method anyway, but we got to know how to do this method so that we can size neutrals as well anyway, so we might as well understand it. So we get permission to apply demand factors. We don't have to use them, but we get permission. And anybody that doesn't would be crazy because it would be in a large, excessively large service if you didn't get to apply some demand factors, okay? Now, I also should note that it says that the general lighting, it may say general lighting, but again, we talked about it earlier. It also does include all the general receptacles that we detail in 220.14J. It includes all of those as well. All right. So let's look at some demand factors here. All right. So we've got all our values on the screen. We have a screenshot of table 220.42. Everything on the screen. And so now that we see it here, we actually can start working it out. So we have the total values. We add them all up. 5,565, 6,000, and 3,000. And I'm going to do it with you. We're going to double check the math. So 5,565 plus 6,000 plus 3,000 equals 14,565. And that's what we have here. Now, what does the code say? It says that we can apply 100% to the first 3,000. Okay. So we're going to do that. So the first 3,000 gets 100%. And then, of course, the next 117,000 is at 35%. So let's take that 14,565 and take 3,000 away because we'll add that later. Okay. We take it away so we can work on the remainder because we already know that the remainder is nowhere near over 120,000 or the next 117. It's not even close. Okay. So I'm taking it now. And so I take that 14,565. I take 3,000 away. That leaves me 11,565. Now, that 11,565, now I get to apply that 35% demand factor to it. And remember what I've told you in previous videos and things that we've talked about, and people listen over in the podcast, when we're using table 220.42 or any calculation in 220, that I am able to take anything that's 0.5 and round it up. Anything that's below that, I can drop off. And so in this case, let's look at the 35%. So another thing that I've told y'all, that anytime I have a percentage, I want to convert this to a decimal point for my calculation. Yes, my calculator probably does it fine, but just get into practice in doing that. So 35%, you start at the right side of the 5, you move it 2 spaces to the left. Now it's 0.35. So that is converting a percentage into decimal points, okay? Now, that equals, so 11,565, that was our new value. So let's do 11,565 times 0.35, and that is 4,047.75. And that's what we've got here. Now, in this case, we have 0.7, so we're going to round it up to 4,048, okay? So it's because we have a 0.5 and larger, we round it. So we have 4,048. Now, guess what? We're going to bring that 3,000 back, okay? So I bring it back, and that ultimately gives me, let's see here, I'll do 4,048 plus 3,000 equals 7,048, okay? And again, just as another example, if you had to use the pure values, then you would have gotten 7,047.75, and you're going to round it up anyway. So it's 7,048 VA. Okay, so now that's your total general lighting and receptacle loads. Okay? Write that down. That's your first hard value. Okay? You've done all the math to this point. First hard value, first step. So now we look and see, okay, we've moved through these. We've covered the small appliance. We covered the laundry. We applied all of the demand factors. Now we're going to start getting into appliances. So what does the code say about that? Now, it says, the term appliance designates utilization equipment commonly built in standard types. Now, this is a definition from Article 100 so that we can kind of understand what appliances are, okay? And so, you know, a washing machine's an appliance, a dryer's an appliance, disposal's an appliance, things like that. Now, ranges are appliances, okay? But they have their own rules in calculating for 220. That's 220.55, okay? So we don't add those here, okay? A water heater is an appliance, okay? Just kind of one of those understanding of what appliances are and all that type of stuff, okay? So you have a garbage disposal is an appliance. Trash compactor is the appliance, those type of things, okay? Just kind of keep the way that we're flowing and understanding it, all right? Now, the dryer is an appliance, but a dryer, clothes dryer, is treated separately because it has its own calculation value under 220.54. You with me? All right, now, again, for the purpose of these calculations, it goes without having to hopefully not remind you again, but kW is the same as kVA. They're synonymous in our calculations. Horsepower ratings must be converted to VA before they can be utilized in our calculation. So anything that I have, these are kind of steps to remember. Any of the motors that we're dealing with that are in horsepower, now we're going to have to convert them down, okay, into an actual VA value, all right? So we want to make sure that I'm going through there and I convert all of my horsepowers, okay? Now, the full load current ratings for single-phase motors, which is obviously what you're going to find in a single-family dwelling, need to be found at table 430.248, and that is going to give you the FLC, okay? Now, there's a tip down here that I refer you to. It says multiply the voltages by the amperes produces volt amperes, okay? So volts times amps equals the VA, okay? All right, anyway, so here, so no D rating is allowed when there are only 1, 2, or 3 fastened in place appliances. You only get to start getting a D rating when you have at least 4. So what does that mean for you and me as a calculation in here? That if I get something that only has 1 or 2 or even 3 fastened in place appliances, then I take it at 100% of its rating, okay? If I've got 4 or more, then I get to multiply it by 75% and take a demand, all right? So if the service or feeders being calculated contains at least 4 fastened in place appliances, the combined VA rating of those appliances, you add them all together, and I'm able to apply a 75% demand to that. And it's based on 220.53. So let's look at our appliances again. We had a water heater, we had a dishwasher, we have an in-sink waste disposal, we have a trash compactor, and oh, by the way, we've got those 3 attic fans, okay, that are going to qualify, all right? Now, when working with appliances, I like to get the VA out of the way, okay? And you should too, because we work in VA. So anytime I've got KW, I want to go on and convert to VA. So a water heater, 4,500 KW, take 4.5 times 1,000. Again, we also can look at it, and since we know it's synonymous, 4,500 KW is going to be 4,500 VA. That one's easy. The next is a dishwasher. Now, on our example, it was a 10. So you saw my example where I said multiplying. So it's 10 amperes at 120 volts. So 10 times 120 is 1,200 VA. Okay, so that's our VA there. Now, we have that in-sink waste disposal, and it's a half horsepower at 115 volts. Okay, so first thing we have to do is we have to go to table 430.248, and I got to find what that actual FLC and amperage is before I can even use my little tip, if you will, where I multiply the amps times the volts in order to find the VA, okay? So in this case, we're going to go to table 430.248, and you'll notice that the half horsepower under the 115 volt column is 9.8 amperes. So once we know that, then we can just go 9.8 times 115. And I'm going to do that with you so that we make sure we're absolutely right. Times 115 is definitely 1,127 VA. So that's what we have here, okay? The next appliance that we're dealing with, and we obviously, folks, are going to have more than 4 or more here, right? So the next thing we have is the trash compactor. Do they even install these anymore? It's 7.5 amperes, and it gives us the volts. So if you get that on an exam or you get that in the real world, again, that's an example of multiplying the amps times the volts, and that'll give you the VA. So 7.5 amps times 120 volts is 900 VA, okay? And then the next thing we're dealing with is the 3 attic fans. Now, they're 4.2 amps each. There's 3 of them, so we're just going to add those together. That results in, they already did this for us, it is 12.6 amperes, and they're 120 apiece. So we're just going to double check the math. 12.6 times 120, and it is 1,512 VA. So we have, again, in this point, all of our VAs. Now, what did it say previously? It said in 220.53 that now that I have 4 or more, that I can add the VAs up, and at that point, I can apply a demand factor. Okay, we're looking for another thing to add to our calculation here. So in this case, it was 4,500 plus 1,200, and I'm doing the math along. You should too. 1,127 plus 900 plus 1,512, and that equals 9,239 VA. And that's what we have right here on the screen. Now, with that value, I'm going to take the advantage of being able to apply my demand factors, a beautiful thing. Okay, there's diversity in these operating devices, or these appliances. So, I shouldn't say devices, these appliances. So, we get some benefits here. Okay, not as much as we would if we did the optional method, but I mean, okay, we're getting something, right? So, what you're going to do is you added them all up. And at this point, you're going to be able to apply the demand factors. Now, how many do we really have here? 1, 2, 3, 4, 5, 6, 7. And here I think it says we have 5. But actually, we have well more than that. I think we just added these up together as 5. But reality, I've got 1, 2, 3, 4, 5, 6, 7. So reality, I've got 7. Okay? But cumulatively, how we added them up together, we have 5 if you were to lump the attic fans together. All right, so at any point, regardless, we have 4 or more. So I'm going to take the 9,239, which if you're following along in the podcast, that was our adding up of the VA. And I'm going to times it. And again, 75%, I could break this down into the decimal and move 2 spaces from the 5 to the left, 0.75. So 0.75. And that equals 6,929.25. Well, that 0.25, that 0.2, I get to drop it off because the code says I can. All right? So, again, up at the very beginning of Article 220, it tells us that if it's 0.5 or greater, you round up. If it's below 0.5, that would be 0.4 and less. You can drop it off for calculation purposes. All right? So, in this case, I have 6,929 VA for my fixed appliances, okay? Now, I'm going to jot that down. That's my demand value, my calculated load now for all those fixed appliances. Now, if you remember, the next thing in our list, we're tackling these things, is the dryer. So we have to tackle this dryer. Now, a clothes dryer, again, is not required for the load calculation, but since it is given, then we have to utilize it, okay? If there's no clothes dryer in your calculation, then you just skip it. You don't add one. Okay, you don't arbitrarily just add 5,000 or whatnot for a clothes dryer if there's not one in the equation. Okay, it's not required. Laundry required except for when the exceptions apply, but a dryer is not. I guess you could literally hang your clothes on a clothes hanger and you're okay. So it's not a requirement. But if it's given in your example, and most dwellings are going to have one, so it's kind of pointless anyway, you got to add it in there. So in our case, the actual stated clothes dryer is 5.5 kW. Well, of course, we know that kW is synonymous with kVA, so we want to convert this. So 5.5 K representing 1,000. We can do 5.5 times 1,000, or me and you know that 5.5 is the same as 5,500 watts, which is the same as 5,500 VA, and it is 240 volts. Now, if one of the circuits on the feeders being calculated is a clothes dryer, then the rating for the dryer must be at least 5,000 watts per 220.54, okay? So now, interesting enough here is that you're going to take the actual value, all right? Whereas if you didn't, you would take it at 5,000, okay? It can't be any less than 5,000. But in this case, the nameplate is higher than 5,000, so we're going to take the 5.5 kW or 5,500 VA, okay? So that's why we're using 5,500, okay, and not 5,000 as it says in 220.54. If it says something on an exam that just says a dryer, then you can't be less than 5,000. So you'd have to take 5,000 if they make statements to the dryer. Now, this is an example where as we're going through this, and I probably should have said this before, all of the loads that are 120 volt loads, you take those values and you make sure you're writing those to the side, because that's what you're going to need for doing your neutral calculation. All right. So it just kind of wants me to remind it here and say that the clothes dryer neutral load on a feeder can be calculated at 70% per 220.61B. But we'll talk about neutrals in a minute. We'll get in those later on in this. So now, if the nameplate rating is more than 5,000, obviously ours is, so we took 5,500. So 5,500 kW is equal to 5,500 watts, which is synonymous with VA, and that's what we want, VA. So it's 55.5 times 1,000. That is 5,500 VA. That's the next calculation we add down. We're adding 55 VA to our calculation. Now, we're moving through this thing. It's pretty simple. We'll look at how this all shakes out. All right? So let's look at the next, what we're dealing with. Now, the next one we're dealing with is household cooking appliances. Now, we're talking about range. We're talking about wall-mounted ovens, counter-mounted cooking units, etc. All these things are household cooking appliances. Now, they're not required, to be honest with you, for a load calculation if they weren't given. It seems kind of crazy to not have them in a dwelling, but because we have cooking requirements to have a dwelling unit, so it seems odd. But I guess you could cook with gas. You have options there, things like that. Now, if they're in your calculation or they're in your question or they're actually in the physical dwelling that you're wiring, then you have to account for them, okay? So, now, if there's no cooking appliances rated over 1 3/4, then there's no need to add anything to the calculation. You know what I'm saying? However, in our case, we do. We have a counter-mounted cooking unit, which is 7 kW, and we have a wall-mounted oven, which is 6 kW, okay? Now, for those that are listening over on the YouTube stream or watching us, if you have questions, I will take a break here in a second and look at your questions, as long as they're germane to what we're talking about. I'm not going to talk about anything that's nothing to do with what we're talking about, okay? I'll just skip over it. Tonight's, again, this is Electrician Live, so this is really geared towards the podcasters, but I want to make sure I answer some questions if I have any, okay? And I'll get us to a point, and we'll do that. Now, for the cooking unit, so 7 kW, 240 volts, and then the wall-mounted oven is 6 kW, which is 240 volts. Now, individual household cooking appliances rated more than 1,750 watts can be derated. If it's less than that, you take it at its full value. I get that question a lot because of the tables in 220.55. You get to apply demand factors when it is over, okay, more than 1,750, okay? But anything less than that, then you take it full value, okay? So, table 220.55 demand factors, and of course, there's a bunch of notes. Okay, a bunch of notes that are on table 220.55 that you really need to be aware of. Okay, now they might not apply in all residential applications, all the notes, but you need to be aware of them. Also be aware of note 4, which is when you're dealing with the branch circuits that are supplying the ranges and cooktops and all that type of stuff. We're doing a load calculation. So we're primarily going to be in note 1, note 2, note 3, that type of thing. But there is a note 4 that reminds you about branch circuit applications, okay? Just be aware of it and that you understand it. All right, now, let's look at it. And again, we're talking a little bit about the neutral. This value is 70% of this range, wall-mounted oven or cooking-mounted is actually what we need for neutrals. But again, we'll talk about that a little later when we're doing neutrals. All right, so let's take the first one here. We have a 7 kW cooking, a counter-mounted cooking unit. That's a cooktop. And we have a 6 kW wall-mounted oven are included in this calculation. Okay, you see what we got on the screen. Now, both units fall within the parameters of actual column B, okay? Because we don't have, theoretically, a range by itself. We have a cooktop and we have a wall-mounted mounted oven. But since these two fall in the middle of, fall in actual column B, then we're okay to use column B in order to be able to do this. And I get to combine these two and treat them as one, okay? So let's look at this, or I combine the values. So let's kind of look at what we're doing here. Since both fall under parameters of Part B, the demand factor percentage found in the column, that column for 2 units is 65%. So I take those 2 units, I multiply the total kW, which is 7 plus 6, and that is 13, and I apply the demand factor percentage of 65% to find the calculated load at 8.45 kW. Now, 8.45 kW is equivalent to 8,455 watts, which is equivalent to 8,450 VA. So I think I said 455. It's 8,450 watts, and that equals 8,450 VA. Okay, so that is our household cooking loads. Now, there's a tip here on the screen. It says, since the cooking calculation falls in both column C and B, be sure to compare the two, okay? You want to look and see which one is going to provide me the lesser value, and I get to use the lesser value, okay? Now, in this case, I am pretty sure that 8,450 VA is less than what I would get underneath the value over on column C, okay, when I'm calculating that for 2 units, okay? All right. So let's look at our equation here and move on to the heat. Now we have the smaller of the two, let's see here, or one of non-coincidental loads. So this is when we get into the heat now and the AC, and we're looking at which one do we discard? Which one do we get rid of? All right, and just literally go the other way. Oh, wait a minute. Let's go back real quick. So let's look at this thing. Now, what I want to do is, while I've got y'all here, is want to take a break, and because I want to go look at something so that we together see if we can see if there's an error in this slide. That's what I think. I can't remember why I did this, but we're going to do this. For those that are listening on the podcast, I'll walk you through it so you can hear it, what we're talking about. We want to make sure that we made the right choice here for the cooking appliances. Now, but before I do that, I'm going to go over and look at some of the posts and see what's going on here and see if we have any statements here. I don't see any. Okay, yeah, okay, nothing that's really too germane to what we're talking about, so we're going to keep going. Now, what I want to do now is I want to jump over, before we keep going, because we're writing our numbers down, I want to jump over and I want to look at ranges again, okay? And let's go ranges. So I'm going to go to the code book, as we have here. And I noticed that Derek says he has his code book today. For those that are watching, Derek is my code book delinquent follower, but he definitely has his code book today. Awesome. So let's go to 220. And I'm going to go to 220.55, this table right here, and see what we've got here. And let's go ahead and get back to me, because half of me, for those that are watching, half of me is blocking up column C. But over on the podcast, what we're doing is we're actually looking at table 220.55, and we want to look at some notes, okay? So what we're going to do is we're going to look at the notes and scroll down, and I'm going to make them come up in the middle of the screen. And what we're looking at is note 3, and we want to look at it. It says, okay, it says over 1 3/4 through 8 3/4. It says, in lieu of the methods provided in column C, it shall be permissible to add the nameplate ratings of all household cooking appliances rated more than 1 3/4, but not more than 8 3/4. And of course, in our example, neither one of those were. They fell right in that sweet spot to use note 3. It says, and multiply the sum, okay, by the demand factor specified in column A or column B for a given number of appliances. We had 2, and we added them together, and we took the sum. Now, again, it says where the ratings of the cooking appliance fall in both column A and B, it says the demand factors for each column shall be applied to the appliances for that column and the results added together. Okay, so if I had something that fall under column A and I had a cooking unit that fall under column B, then I would solve A and I would solve B, okay, and then add the sums together, all right? Okay, but again, in lieu of. So the reason we're doing this is because under C, they both fall under C, but 2 appliances would have required 11 kW. And of course, because we could apply demand factors, because they both fell under B, then in our case, we were able to apply demand factor, and that's why it resulted in less, okay, for our application, okay? So we applied 65, oops, sorry about that, folks. We applied 65%. So we compared the 2, all right? And we looked at the 2, and we determined that by looking at the 2, that use of column B was it resulted in the smaller value, okay? So that's why we used column B, okay? So that's what I wanted. I remember now that I wanted to use that to highlight it because I wanted to be able to explain to you what happens if it falls under 2 different columns, okay? Solve each one independently and then add the values together, okay? And I can do that in lieu of using column C. Now, if column C is the better value or the better result, then I'm going to use column C, whichever gives us the best result, okay, the lowest result, okay? All right, so again, I just want to make sure I reiterated that for everybody. Okay, so that's a value we write down. So we had another value that we jotted down, and that was the cooking. Now let's move on to the one that causes people more confusion, and this is we get to take the lesser of, actually the larger, I don't know why I say lesser, the larger of the 2, we compare the 2, okay? And we get to discard the one that's the less, okay? So, we get to do that. So let's look and work this out. So the smaller of the 2 non-coincidental loads gets to be omitted but they're not supposed to be non-coincidental means they're not designed to run at the same time. There's some kind of fail-safe mechanism, thermostating system, whatever that keeps the 2 from operating at the same time. However, I will remind you that air handlers will be operating either or, okay? So it doesn't really matter. They're going to be going all the time, whether it's heat or AC. So kind of things to remember. All right, so 220.60 is what tells us that we can omit the smaller and take the larger. Okay, by definition, non-coincidental means not occurring at the same time. A dwelling's electric heating system and air conditioning system may not be coincidental loads. So you have to be careful, because this only applies if they're non-coincidental, okay? So, you gotta know that what you're dealing with. So, the heating system and the air conditioning may be non-coincidental loads. Most of the time they are, but you gotta be careful, okay? Just know what you're doing. Normally it is, and we don't have a problem, okay? So now let's look at this here. We had the air handler, that's the blower motor, which has a rating of 368 VA, which is this one. So we're going to test ourselves. We got 3.2. Let's do it together. That is this one right here, folks, times 115, and that is 368 VA. So that's right. Then it says to get the value we calculated 3.2 times 115. That's what I just did on my computer. or my calculator here. Now, since both loads are energized simultaneously, add the air handler to the 15 kW heat as well, okay? So, in other words, when we mean simultaneous, it means that when that air handler is going and the heat loads are going, they are going to be going at the same time, okay? But the air condenser will not, and the air compressor will not, okay? But that air handler will. So you have to make sure that I add that value to the heat when we're comparing it, because it's got to blow that warm air, right? All right, so, and it's just easier to understand the concept here, all right? So in this case right here, and we're talking about electric heat directly, not a heat pump, electric heat directly, strip heating we're going to use in this example, all right? If it's a heat pump, totally could be a little bit different because you would have the outside condenser fan motor going, okay? But in our example, we're going to say it's not, it's separate electric heat to make it simple for the calculation. Just be aware of that and the realities of real life, okay? And it's just as simple of making sure you add in the loads that you know will be running, okay, when you're comparing. It's not complicated, but we wanted to make it simple to be able to do it in a presentation. So 15 kVA, and make sure we add the blowers as well. So that would be 15,368. That's the 15 kW, which is 15,000 VA plus the 368. Now, fixed space heating loads are calculated at 100%. That's what we've done, and that's what it was. Now, air handler blower works with either the heat or the air conditioning, so that's why we added it, and it gets added to the both calculations. No, so now we know the heat. Now we need to look at the AC. So the AC compressor is 16.6 amperes. So 16.6 times 230, because that's the value that's given. Another tip, do not bring common sense into your equation on an exam, okay? Take the values that are given if you're preparing for an exam, okay? In this case, it says 230 volts. That's what the appliances we're dealing with. And guess what? There you go. You need to take it at the 230 volts, all right? Okay, back to the equation. All right, so 16.6 times 230 volts, that is 3,818. Don't trust me out there, folks, that are listening. Do 16.6 times 230 and see what you get. It's 3,818, so we are correct, okay? I tell people this all the time. Don't take what I say as gospel. Don't take what anybody says as gospel until you do it and you're convinced. Once you're convinced, then you're wholeheartedly in it, and you're in it to win it, okay? Boy, that's cliche, isn't it? But it is what it is. Okay, now, next we're going to look as part of this air conditioning is the condenser fan, and that's at 2 amps. We saw that right here. So that's at 2 amps, so we already know that value. So we do 2 amps times 115 volts, and that's 230 VA. So I'm going to check myself. 2 times 115 is 230 VA. So we're just adding up these numbers now. The next and lastly, we have the air handler again at 368 VA. Okay, 368. Okay, we did that calculation earlier, so you know how we got that. It was 3.2 times 115%. We already did that, so that's how we got it. Okay, so for a combined calculated load of 3,818 plus the 230 plus the 368 equals 4,416 VA. Well, what do you think? That heat is about 4 times or 3 times or some odd, 3 times and some odd cents or whatever it is, more than the AC. So guess what? If we size it and calculate our load to the 15, don't you think in the summer when the AC's running that it's not going to pull nearly that 15? So if we design for the worst case scenario, we're okay. Now, incidentally, there are some changes to the 2020 code that says, you know, whatever motor, if the motor with that AC happens to be the largest motor of all of the motors you're dealing with, then you at least take that motor's value, but, you know, and do that at 125% and all that good stuff. But that's not the case in the 2017. That's not what we're doing here, okay? So we're simply taking and it might have been what they intended, but that's not what it says in the code. So here we're taking the heat. So guess who wins? The heat wins. So that is 15,368. So remember, we're stacking these things. All right, now, here's a tip. A heat pump with supplementary heat is not considered a non-continuous, is not considered a non-coincidental load. Okay, so anytime we're dealing with a heat pump with supplementary heat, it is not considered a non-coincidental load. You have to add the compressor's full load current to the maximum amount of the heat that can be energized while the compressor is actually running. It's kind of what I was talking about earlier. You have to make sure you add those values in there. Okay, remember to include all associated motors as well, blower, condenser, and everything like that. Okay. In our case, we don't have a heat pump. We have an air handler unit with a cooling, air conditioning package, a coil, and outside unit, and we have individual electric heat. Okay. All right. Now, next thing we need to do is we need to say, okay, what is the largest motor in this dwelling? Because I need to take the largest motor at 25%. Okay, we've already done the calculation on the motor, so I need to take the value. I need an additional 25%. Is basically what I'm doing. Okay, because we already accounted for the motors. Okay, we just need to add this additional 25% based on 220.50. Okay, so, and you know what? The air conditioning compressor might be the largest motor. Okay, so because that's what it says in 220.50. So let's look at what we got on the screen. It says the largest motor is usually the air conditioning compressor, and based on 220.50, and it's referenced in 440.6, which is HVAC applications in Article 440, it would be used to get the 25%. However, in the case, in our calculation, since the air conditioning load was omitted, we would use the second largest motor in this dwelling. In this case, it was the in-sink waste disposal, and we'll look at the values here. Now, this brings me again to an interesting thing. The 2020 code says it differently, okay? The 2020 code is going to say, you know what? If that air conditioning compressor was the largest motor, even though it was omitted, if that is the largest motor in the actual dwelling, then I would take that motor at 125%. Okay, because we omitted it, and it wasn't like the other motors that we calculated, like trash compactor and attic fans and all that kind of crap, right? But that's 2020 code. That is not 2017 code. So remember, that's why it's so important to learn the changes to the code, because there's some changes that take place within the 2020 code. Okay, all right, and that's all I'm going to talk about 2020 code tonight, because we're very much in the 2017 code. All right, now. So let's look at each of those motors that we had. We had in-sink waste disposal motor as a 0.5 horsepower. And we knew that was 9.8 amps times 115 volts. So that's on 1,127 VA. Then we had that trash compactor, which was 900 VA. And then we had those 3 attic fans at 4.2 amps. And it's each motor. We take each motor, okay, because they're individual, because we're looking for the largest motor, not the largest collection of motors. So it's 4.2 amps times 120 is 504 VA, okay? So in this case, we see that the in-sink waste disposal is the largest motor. So we take that 1,127 VA times 0.25 or 25%, and that gives us an additional 281.75. And remember that 0.7, anything 0.5 and larger, we round up. So now we have an additional to add to our calculation is 282 VA, okay? Now, the dishwasher is an appliance at 1,200 VA, and why it is not used is because it is listed in 422 as an appliance, and we typically would not take the actual dishwasher at its value as a largest motor. But we would take it because the dishwasher doesn't get rated in a motor type of rating. It actually is encompassed in the actual appliance, and it's all figured in, and we already calculated it in our calculations, and we actually gave it a demand. Okay, so we wouldn't typically use that as one of our motors. Okay, so we've got an additional 282 VA that we've added to our long list of calculations. So let's do a double check here and see what we have. Did we cover the square footage? Yes. Did we cover the small appliances and laundry brand circuits? Absolutely. Water heater, check. Let's see here. The dishwasher, check. The in-sink waste disposal gave us a horsepower rating, check. We calculated and converted. Trash compactor, attic fans, clothes dryers, cooking, heating strips, air handler. Yep, we've got everything. Okay, so now it's crunch time. We're taking all those numbers. We did our general lighting and appliance. That was 7,048. You remember that? You wrote it down. Okay, you wrote it down. And it also includes what? The general lighting, the small appliance, and the laundry brand circuit that were all calculated. And we applied some demand factors to that based on 220.42, right? And that was the 7,048 VA. The next thing we did was the fixed appliances. And that's where we had 4 or more, and we were able to apply 75%. So it was 6,929 VA. That was what our actual calculated load was after we applied our demand factors. We had the clothes dryer, again, where there is one installed. In this case, it was. So we took the 5,500 VA at its value. And then we had the cooking appliances. And remember, we calculated those up. They were all under column B, 2 appliances, 65%. And we ended up with 8,450 VA. And then lastly, we compared the heat to the AC. And guess what came out on top? The heat came out on top. Okay, so the heat is larger than the AC, so we got to omit the AC. And then we talked about how that changes in the 2020, at least for the motor, but that doesn't apply for you in 2017. So then we had that largest motor, true motor, not an appliance built into like the dishwasher. Okay, all right. So and then the next person will say, well, how come you took the trash compactor? Because that's a pure motor load. It's a compression compaction. And again, that's just, we do. Now, if you wanted to take let's say you made the mistake and you wanted to take the dishwasher. Let's just for craps and giggles. Okay, that was, and I'm going to do this because I like to do this when people ask. All right, so if we took that value of the dishwasher, it was 1,200 VA. Okay, and we took 1,200 VA times 25%, that's 300 VA. So it's not going to change our equation worth a hill of beans. 282 versus 300. I'm just telling you, we do not use, for whatever reason, we do not use the dishwasher. But if you want to, go for it. It's not going to hurt anything. It's not going to change our overall value, I can promise you. All right, so now we add all these up. And, of course, you can agree to disagree with me. Perfectly fine. All right, so it's 7,048 with 6,929 plus 5,500 plus 8,450 plus 15,368 plus 282 equals 43,577. Okay, now, since this is single phase, 240 volt, and we're sizing services, so we're going to take that 43,577, and now we're going to get into good old Ohm's law and all that good stuff, is we're going to take the VA and we're going to divide it by 240. So I'm going to divide that by 240, and that is 181.57. And of course, since it's 0.57, we're going to round it up to 182, again, due to that 0.5, which is referenced in 220.5b if you want to know where the rounding rule comes from. Since it's in 220, obviously all calculations that are associated with 220 are going to be privy to that ability to round. Okay? All right. Now, if that's the case, we now need to go and find out what the minimum amperage rating required for our service and feeders that was being calculated. So, in this case, the service or feeder overcurrent protective must be higher than the number found in line a standard ampere rating for a fuse. So, in our case, we had 182, right? So, in 182, nothing corresponds in 240.6a, right? So, in our case, we went up to a 200 amp device based on 240.6a, Okay? Now, everybody might say, well, okay, so that's our device, but what about the conductor sizes? Well, remember, since this service is actually falling between 100 and 400 amps, and it's a single family dwelling, and all that good stuff applies, then and only then do we get to apply 31015B7. In our case, we're going to use B7.1 because we're dealing with a service, okay? If it was a feeder, it would be B7.2, okay? Incidentally, I said I wasn't going to talk about 2020 code, but this is 310.12 in the 2020 code. I just felt like throwing out there for you the change, okay? All right, so now, let me just make something clear. If you wanted to size the conductors for 200 or whatever at full size or full rating, go for it. On an exam, for example, they want the best possible answer, okay? Best possible answer. So, since we can apply 31015B7, it says, for a service rated 100 through 400 amps, the service conductors that are supplying the entire load associated with a one-family dwelling, or the service conductor supplying the entire load associated with an individual dwelling unit in a in a two-family or a multi-family dwelling, shall be permitted to have its ampacity not less than 83% of the rating of the service, okay, or the service rating. Okay, now what is the service rating? It is the values that are given in 240.6a, okay? So if the breaker is a 200 amp, then that is your service rating. If the feeder is feeding a 200 amp breaker, then that is your service rating, okay? So here it just allows us now, 310.15B7 used to have this little table, which is a quickie table. Then it disappeared. Then it ended up back in Informative Annex D for calculations, okay? Now in the 2020 code, it's back again. But all of this was based on the 83%. And then remember, to use this, all the rules have to apply, okay? So let's do it. So if it only applies up to from 100 to 400 amp services or feeders, okay? That's the window that this applies. Now, so the minimum size service or feeder rating, which is 200 amperes, okay? Now we're sizing conductors, and it can't be less than 83% of the service rating in this case, okay? So the service rating was 200 amps. So we're going to take the 200 amps times 83%, or 0.83. And that is 166. Okay, now, then I want to select the conductor from the 75-degree column, which is 31015B16, that will handle, okay, 166 amps. And so I go there, and you'll notice that it's a 2-aught, okay? And again, always assume copper unless it states otherwise, so we are assuming copper. And a 2-aught is good for 175 amperes. So this is the minimum size conductor that's acceptable if all the rules in 31015B7 are followed, okay? Now, if it's an aluminum conductor is your choice of flavor under the 75-degree column in 31015B16, then the ampacity for a 4-aught aluminum conductor is 180 amperes, which will also work just fine, okay? So this is how you've got those little values in the table, which you didn't have to do a calculation. The 83% rule is how that table was derived, okay? And so the reason that the table went away originally was because we did not want people to actually get confused and think that this table was a catch-all, because you do have certain things like conditions of use, like elevated ambient temperatures and things like that, that you still have to account for. It's because it's not a perfect world, okay? But in a perfect world, you could pull just like we just did, and that would be the sizing of your conductors, okay? Now, if you have adjustments or corrections, and you're probably not going to have adjustments for more than 3 current conductors, probably not in a dwelling, so that one's not going to come into play. But you might have an ambient, okay, that you have to do a correction, okay? And so you might have to do that. But you typically, most people don't. They don't think about it. They just don't do it. But you need to know how to do that. And I encourage you to go watch my D-rating demystified video. if you want to learn how to do adjustment and corrections. And we're going to update that for the 2020, and it's going to be over on our Patreon page. Okay. I have a bonus question that I usually ask people, and that says, what is the minimum size for the grounding electroconductor to the water pipe ground? Okay, and assuming it's supplemented, means it has maybe ground rods that are supplementing it. So when I do this, I'm going to size the grounding electroconductor based on table 250.66, based on the size of the service conductors. Okay, and in this case, they are 2/0 copper, right? So actually, let's do that. So I'm going to go to the NEC, and when I go to the NEC, and I see all of my people that follow over on the video stream I have a sharp bunch of people. I only hang out with sharp people, by the way, and all of the people that follow me that actually listen to our stuff is sharp people. They know I love them. And so we're going to go over to 250.66. And I'm not like most educators. I actually do appreciate the people that learn from me. Okay? I'm just saying. All right, so here we're over here, and we said, now let's see here. I want to make sure that we said it was 2/0 copper or 4/0 aluminum. Okay, so if we're dealing with copper, it's 2/0, it'd be right here. And it's a water pipe ground, it would require a 4. So possibly the folks over on my YouTube stream picked the wrong conductor, because it's based on the size of the service conductor. So here it was a 2/0, so it needs to be a 4. We didn't say ground rods. We said water pipe ground. Okay? All right, so a 4. So I can do this to all them over there that might have got that wrong. I will do this for them. Okay? And if it's 4/0 aluminum, right here, it's also going to be a 4 copper or a 2 aluminum. Okay? All right. All right, so let's get back to the PowerPoint presentation. I'm not going to hear the end of that one, okay? All right. So now, that disappearing table, again, I wanted to show you some kind of the graphics of how this would look. And so this is an example where the power comes in, and it hits the panel. And this is where we could apply that value, that 83%. So like we did, 200 times 0.83 is 166 amperes, okay? Now, if it doesn't handle 100% of the loads, then I can't apply 31015B7. So what would you do? You would just use the regular ampacity values that are in 31015B16, okay? We're using this to give us an advantage. If it can't meet the rules, then I can't use the advantage. You with me? All right. So here's another example of where I could use the actual 83% rule, or the allowance of this. So say I have the service coming in, and let's say this is a situation where I have the emergency service disconnect now required in 2020 code. I said I wouldn't keep saying 2020. But let's say this is on the outside of the building, and of course, it also applies to 2017. If I want the panel to be further into the building, then I have to put outside or nearest point of entry on 230.70A1. So in this case, I've got the service disconnect outside, and I've got the remote panel inside of the actual dwelling. Okay, well, see this? If this panel right here in this feeder is seeing 100% of the loads, so it's simply feeding through, then I can apply the 83% to here, and I can apply it to the feeder, okay, the feeder conductors as well, all right? And then I'm okay, as long as I meet those rules, all right? So like we did the example, and I'm going to go through this, and we're going to go to neutrals in a second here. So you see what I'm doing here? If these rules apply, I can do it. If not, if the rules don't apply, have no fear, don't panic. Then you just size it at 200 amp rated breakers, and you go to 31015B16, and you size whatever conductor can actually handle the 200 amps. And I believe if you didn't use this, then it would require you to have a 3/0 copper instead of a 2/0 copper. Not the end of the world, but there is an advantage to being able to use 31015B7, okay? All right, so now let's look and see what we're doing for the neutrals. So here, again, everything's the same. Nothing changed. The only difference is what I've highlighted are all of the things that are neutral loads. And all of these have to be considered when sizing the neutral, okay? So again, all of those calculations that we did up front for the dimensions and the 7 times the 10 that we took out and the 4 small appliances and laundry, all of those are utilizing 120 volt loads. So there's a neutral involved. So we got to calculate that's a neutral, all right? All the 240 volt loads don't utilize the neutral except for the clothes dryer and the cooking appliances, and we're going to take those at 70%. So I don't have them highlighted here because they're going to be treated separately in a second. All right, so remember that general lighting load that was 7,048? Well, that's all neutral load, so I'm taking that. Now, remember of the appliances? Well, the water heater doesn't count, but all the other ones count. They're all 120 volt loads, right? So we already did all this and we knew it. The only difference here is we took out the water heater, okay? We took that out of the equation, all right? So in our case, it was 3,554, okay? Now we want to make sure that we're right with that. So I'm going to do some calculating, make sure we're right. 1,200 for the dishwasher plus the in-waste sink disposal, which was 1,127. You can do this with me and make sure that I'm still on this so that everybody can see it. Okay, yes, I am. Okay. Plus, we're going to now add the trash compactor, which was 900. Plus, we had those 3 attic fans. And again, we can go back now to adding them all up together. So that's 1,512. And that is 4,739. Well, guess what? I still get to apply the demand factor to this as well. Okay, I still have 4. So even though it's a neutral, I still get to apply it. So that would be times 0.75, and that is 3,554.25. That 0.25, I drop it off, and I just take the 3,554. Now, again, I get to also go on to looking at the clothes dryers, the cooking, and the wall mounted. We said we were going to tackle this, okay? So the 5,500 is 5,500 watts. That's 5,500 VA, okay? And we take that at 70%. So 5,500 times 0.70, and that is 3,850, okay? So we write that down. That's our neutral load. The next we had was the 7 kW counter-mounted cooking unit and the 6 kW wall-mounted unit, okay? So we already did this calculation already. We'd already done it, okay? So we take that 8,450 VA times 70%. So 8,450 times 0.70, that is 5,915. Write that down. So we have value. So what do we got so far? We've got 7,048, 3,554, 3,850, which was the dryer, and we have 5,915 VA. That was the cooking combined. Okay. Now let's look at the AC versus heat. Okay, because remember, when the AC is running, okay, then we do have some loads that could be running here. So in this case, remember the little exercise that we did with the AC versus heat? So let's kind of work this out because we do have neutral loads that we do want to take into account, okay? Because they will be running when the air conditioning is running. So when we're doing neutrals, we definitely want to count that load, okay? Remember that heat? That heat was 240 volts. So when the air conditioning is running, we do need to take the neutral count because there is going to be neutral loads. Now, the air compressor we get to ignore because that's 230. We don't worry about that. So it was the compressor unit, or the condenser unit, I should say, or excuse me, the condenser fan motor at 2 amps times 115 volts. That was 230 volts. You remember we did that earlier. And you remember that old air handler, 3.2 amps times 115? That is 368 VA. Okay, now they will be running again, regardless of what's going on here, okay? If the AC is running, both will be running. If the heat's running, you know, the condensing fan will be running. The air handler motor will be running. When we're doing AC in the summer, We've got neutral loads. Obviously, the air handler is going to be gone and the condenser fan is going to be gone, and it is a neutral load. So that's why we're doing the neutral loads, okay? This is a little different than comparing heat versus AC for the actual load calculation. We're not comparing here. We have to take all of the neutral loads, okay? So the heat was larger, but the AC still has neutral loads, and we're sizing neutrals now, okay? That's what we're doing. So that's how we came up with it. So 230 VA plus 368 is 598 VA. So that's another thing we write down. Now, the last thing we need to calculate, again, is that largest motor, and that largest motor that has the neutral loads. So let's look at it again, and remember, we're using 115 volts or 120 volt loads. So of all these, remember that in-sink waste disposal was the largest. Remember, it still applies. So we take that value again, and we're just simply taking it, that extra 25%. So you multiply 1,127 times 0.25, and that's going to give us the neutral load of 282 VA contribution, okay, to the neutral loads. So that was all of our items in there. And so now we're going to do it kind of a wrap up of this. So again, we got our general lighting appliance. That was 7,048, if you remember. We've got our fixed appliances at 3,554. And the only difference between the other is we got rid of the water heater. We got the clothes dryer at 5,500 VA, but we got to take that at 70%. So that was 3,850 VA. We had the cooking appliances, which we added together because they were both under column B, and we applied 65%, and that was 8,450 VA. But then it says in 220.60 that we can take it 70% of that for the neutral. Okay, so that's 5,915 VA. And then, of course, we had the air handler motor and condenser fan motor, which definitely were neutral loads, and that is 598 VA. And, of course, we had the largest motor that we're also taking that value at 25%. So that is 282 VA. So we add all this up. Now, at the end of the day, I'm just going to tell you, in the real world, if you leave off or mess up when it comes to the largest motor, it's probably not going to change your value, okay? It's probably not going to change anything, and I'll show you that in a second in case you screw up in real life. All right, so 7,048 plus 3,554. We're just checking our math here. Plus 3,850 plus 5,915 plus 598 plus 282 equals 21,247. Now, you divide that by 240, and that's going to be 88.52. So obviously the 0.5, we're going to round it to 89 amperes, okay? And that's what we're doing, and that's the size, the minimum size. Now, of course, we do have requirements in the code under 250.102C for minimum sizing of the neutral conductor. So you gotta be aware of that table, okay, at the minimum size. But also, you also had to calculate the neutral load, okay? And so whichever is larger, you got to go with, okay? So again, usually it's going to be larger than what would be required in size for the actual 250.102C when you actually do the calculation. But you need to compare, okay? So in this case, we know it's 89 amps, okay? Now, just to do it, I'm going to leave out the 282 VA and to show you what happens. So I'm going to take the 21,247 minus the 282, and that is 20,965. I'm going to divide that by 240, and that is 87.3. So that would be 87 amperes. So it's a difference of 2 amperes, okay? Not going to be the end of the world when we size the conductor, okay? You'll see that, okay? So 89 amperes. So for us, if we were to go in the code, since we're sizing it, we might as well do it. Let's go into the code. We'll go to the NEC. And we're going to go at this point. The first thing that I like to do is I'm going to run down here to here. And you see it says grounded conductor right here. So the largest ungrounded conductor is, in this case, was the 2-aught. We determined it was 2-aught. So it's got to be at least, if it's copper, it's got to be at least a 4. Okay. If it was a 4-aught, then it's got to be at least a 2 aluminum. Okay. For my grounded conductor. Okay. Or our neutral. Now, we still have to base it on the calculation. So at this point, we know that it was 89 amps. So what we're going to do is we're going to go now back to 31015B16. And we're going to look and select a conductor under the 75-degree column. And we'll just say copper. And we're going to go and we see something for 89 amps. And it looks like 85. But in this case, it's a 3 gauge. So it'd be a minimum of 3. Now that's interesting because in this one, we probably could, I think it was 87. It still would have put us over the 4, so it will put us in a 3 gauge. So you see there, it was close, but it didn't make a difference whether or not you do that or not, okay? So in this case, it would be a minimum of 3, all right? And again, 3 is going to be larger than the 4, which was required in 250.102C1, but we based it on the calculated neutral loads using the standard method, mind you. Can't use an optional method to do that. And that's how we came up with our sizing for the neutral conductor. All right? Now, again, here's what we did. 21, 240, 89. We went and saw that it's a 3 copper. And it was a 2 aluminum, and I just did that. I could have flipped the screen, but now I'm honest. I kept myself honest here, so that's what we did, okay? So anyway, let's take it back to me. And that was our presentation for tonight. Let me get it back to me, okay? And that's just kind of giving you all the necessary concepts. Again, we can dig into the weeds of certain things, like whether it's heat pumps and everything, but my point with you is if you take it systematically in treating it, so even if you were to do all the other things, right, and then you got to the application for the heating versus cooling, and then you slowed down at that point and determined whether or not you had heating, which was just separate heat, or it was a heat pump, and it's just percentages. It's just values. It's not complicated. All right, but I wanted to give you the basics of how you apply it, and that's what we did here. So I went a little long tonight in the show, so I just want to make sure you cover everything, that you understand it. And so now I'm actually going to end the podcast, but I will stay on to answer some questions in the video stream. So people on the video watching on YouTube, you stay in here. I'm just going to leave the actual podcast. So everybody on the podcast, thanks for joining. Until next time, stay safe and God bless. You've been listening to Electrician Live with your host, Paul Abernathy. All right, so we're back to the video stream, and so I'll try to look and answer some questions that we have here that are in our presentation. Let's see here. Ronbo, again, shout out to everybody that came in tonight. I've covered a lot of you earlier, but I want to say also catch up and say, Derek, thanks for coming. Matt A., Ronbo, Nick, thank you for coming. Lightning Electric, thanks for joining our live stream. Mohammed, thank you. Thank you. Incidentally, your stickers went out today, my brother, so I've got them for you. Nick's question is 60 or 75 degree. Which one is used? You always are going to use the 75 degree in this case, unless they tell you otherwise. But all of the terminal ratings that are involved here are 75 degrees C, okay? And also, the ampacity values that we're dealing with in the service are all over 100. So it's actually going to be the 75 terminal limitations anyway, okay? Let's see. Following up some questions. Caleb, you can watch the rebroadcast because this was Electrician Live. And so right now I'm just kind of staying on here a little bit. Don't want to be too long because then people won't watch the whole video. Believe it or not, people only watch like 20 minutes of a video or even 10 minutes. Statistically, if somebody watches your video for 5 minutes, you're doing really good. You know my videos are long. If y'all aren't watching the whole video, then I don't know what people are getting out of my videos. I mean, I like to watch the whole freaking video, but that's just me. I have a greater attention span and that type of thing I get. Can we download these slides? No, you can watch the video. I can't give you the slides. Am I going to put this video up on YouTube? Absolutely. It will be available so you can watch it. Again, if you want. Okay. So that application. Now, Matt, you probably do want me to visit cooking appliances, but I am not going to tonight get into all the notes. And I'm sure that's what you want. You'd like to look at it when an appliance applies the 5% for every kW over. Not going to do it tonight. We'll do that another night because this is Electrician Live night. And I don't want to be on too long because we have people that listen to our Electrician Live. And so I don't want to get into all of those nuances. That's usually something we do during the week. So maybe one day during the week, this week coming up, I will do maybe ranges a little more in detail. And we'll look at ranges and how the notes apply and things like that. So those that are following, stay tuned for that next week. Again, I'm usually on during the week and you can listen, okay? So that is the single family dwelling. I want you all that if you have questions and how other things may apply, then be sure to bring those questions during the week when we're doing code sessions, okay? Today's presentation was just the basics of single family dwellings, okay, in the calculations. I will do this as well for optional methods at another point because, again, other than an exam, which is mainly going to be on the standard method, optional method is how we are probably going to really do it. That's the way we're really going to do it, okay? So just remember that. And let's see, any questions before I go? Let's see, 12 Mandingo says, let's say we got a tankless water heater we want to add to the house. My understanding is we would want to do the load calculation to see if the service can handle the new equipment. You would, because some of those tankless water heaters can pull quite a bit. The good news is most of the manufacturers for tankless water heaters will give you the maximum size service, but that doesn't necessarily mean that you still have the capacity. All right? So you definitely want to do a calculation to make sure that you can add it into the equation, into your load. Again, it is just an appliance, so you will treat it as such because it will have an actual value, okay? If it has amps, you know now how to calculate that. Amps, okay, is the equation itself is pretty easy to come up with what the VA is. You with me? Okay, it's just the amps times the voltage equals the VA, and you can do that, okay? I had a tankless water heater on my house prior to moving to Texas, and it was one of the early sets models, and it was great until it got to a point, and then the regulator went bad, and the daggone thing would scald you during a damn bath, or it would freeze you during a bath. You never knew. So I ended up yanking it out right before I left and put a regular water heater in it because it was just like, but now they got really good ones now that are a lot better. And it has to do with the groundwater and the rate of flow and all this kind of stuff. But mine was an early one. It was called a sets unit, and it was back early when they started coming out. So I'm sure they got much better. They have digital controls now. So again, but yes, you want to make sure that your service can handle that load, and you would need to add it to the calculation, just like an appliance, just like we added the water heater to the appliances, okay? Same thing. Make sure you add it in, okay? All right, guys, well, I'm going to go tonight because I have to be with the wife tonight. And, so I will do a shout out real quick again. If you want to see what's changing in the 2020 code and you want to follow me in that journey, then you can join our Patreon, which you can go to paulabernathy.com and it'll give you the instructions. You don't have to be a VIP. You can be, a 5 because it is a monthly commitment. What I would say is anybody that's joining, wait until the 1st to do it. Because if you join today, it's going to charge you the full amount, and then it's going to turn around and charge you again in one day. Don't do that. Just wait until the 1st and do that. Okay. If you're at the end of the month and you want to join, say 2 weeks to the end of the month, then I recommend doing the $5. And then if you want to be VIP, wait until the 1st of the month, and then you can jump up to the VIP. That's up to you. You do whatever you want, but I'm just trying to save you a little bit because it will automatically debit. And I appreciate that ongoing support. I really do. And that's where we're putting all of the 2020 stuff at. Okay. So, I think when you price it, if you think about it, $5 is the minimum for a year. Is cheaper than you would get a book on the 2020. Plus you get newsletters and other stuff. You get my code update newsletter, all that stuff, and you get discounts on goods, and there's other stuff that we'll be putting in there. So it's, if you don't want to be the VIP, then go with the lower level. That's up to your budget, whatever you want to do. It's not up to me, whatever you want. If you don't want to do it, don't do it. Also, I want to do a shout out and say, guess what? Our 2020 residential and commercial course has been updated for the 2020 code. I've added a lot of good goodies in that. That is available for purchase now. It did have an increase in price from $315 to $335 because my LMS background went up. So it went up, and so I had to raise it up as well. I think it went up $15. So, but it is there. If you really want to get an in-depth understanding of all residential things and how codes apply and the general rules and thumbs and look at it room by room by room by room, then there you go. If you're a commercial guy or you're transitioning to commercial program is amazing, okay? And I had a hand in writing those books. So, again, I'm excited about those. All right? Anyway, the fast tracks for 2020 will be updating as well, probably in the next couple of weeks or maybe even a month or two. Again, but that's only going to be if you're in the 2020 code. So we've got time for that. Mostly the normal fast tracks that we have now is going to serve most of the country for the next year anyway. But I just want you to know stuff that we're working on. That's stuff down the road, okay? And I think that anybody that uses a fast tracks program to prepare for an exam and you don't pass your exam and you really use the fast tracks properly, then I don't know, something wrong with you. All right, folks, till next time, I appreciate all of you. And until next time, stay safe and God bless. You've been listening to Electrician Live with your host, Paul Abernathy.